In this first build on the channel, we're creating a 3D printed 5-inch FPV freestyle drone from the ground up. I begin by showcasing the design of each printed part, then walk through the printing process and how the parts come together to form a complete frame. Next, I go over the components selected for the build and how they're integrated. Then I move into Betaflight to set up the initial configuration. Finally, I perform PID tuning based on test flights and black box log analysis to extract the best performance from the build. Alright, let's get started. I used FreeCAD to design all the drone parts. This is the main fuselage. Its purpose is to house and protect all the electronic components of the drone, except the motors. The enclosed structure provides solid protection and a clean mounting base for everything inside. Here you can see the planned layout for each component. On the top side of the frame, there's space for a 1400 to 1550 mAh 6S battery, a XT60 battery connector, a status LED, and, at the rear, a GPS receiver. If we look at the bottom side of the frame, there are dedicated mounting areas for the flight controller and ESC stack, the radio receiver, and the radio antenna, positioned inside the frame for protection. There's also space for the digital video transmission module and its antenna, both integrated within the frame. At the front, there's a camera mount with adjustable tilt, allowing you to fine-tune the camera angle for your preferred flight style. Okay, next let's take a look at the drone arms. In this build, the arms are fully replaceable, just like in most carbon fiber frames of this size. That means if one breaks, you don't have to reprint or rebuild the entire frame. Just swap the damaged arm, and you're good to go. The arms do more than just hold the motors. They're also the main path for motor vibrations, carrying them through the frame all the way to the flight controller where the gyro sits. That makes stiffness really important. If the arms flex too much, those vibrations can interfere with flight stability. At the same time, they need to stay lightweight so they don't drag down performance. These arms are mirrored, meaning the left and right sides are exactly the same, which keeps things simple when printing or assembling. The only deliberate asymmetry is at the front. The tip of each arm is slightly shortened to keep the propellers out of the FPV camera view, giving you a cleaner, less obstructed image. Next up is the bottom cover. It protects the electronics and needs to be strong enough to handle rough landings. At the same time, a bit of flexibility helps absorb hits and reduce vibrations going into the frame. It's a balance between being tough and slightly flexible to protect what's inside. The last frame part is the battery cover. Its main purpose is to make the drone more aerodynamic and give it a cleaner look. It doesn't actually cover or protect anything. It's a very thin print. It's simply pushed into place, and as it flexes slightly, it locks itself in securely. Okay, it took a fair bit of trial and error to make sure each component fitted properly. Now that the design has been finalized, the next step is to export all the individual parts into a format that can be used with a 3D slicer. In my case, I use Bamboo Studio for slicing and preparing the files for printing, so I'll be exporting the models in STL format. I'm using the Bamboo Lab X 13D printer with the AMS, Automatic Material System. It comes with Bamboo Studio, which is the slicer I'm using here to prepare and print all the parts. The software offers a wide range of settings and controls, making it possible to fine-tune the final properties of each part, whether that's strength, surface quality, or weight of the part. The main fuselage is the heaviest part of the build, but it also needs to be strong enough to withstand crashes and protect the internal components. Since all other parts are connected to it, it's also the most difficult piece to replace if damaged. To meet those demands, I'm printing it with PLA CF filament. It's a carbon fiber reinforced PLA that offers increased stiffness and durability compared to regular PLA, while still being very easy to print with. The added strength makes it a good fit for structural parts like this, where both rigidity and print reliability are important. Since I've installed an LED inside the fuselage to indicate the drone's status, I needed to add some level of transparency to the part. The LED will be positioned toward the rear of the drone. I'll cover that in more detail later. To let the light shine through, I decided to add a few transparent PLA stripes to the fuselage. Thanks to the AMS unit, I can load and use up to 4 different filaments at once, which makes it easy to combine materials like this in a single print. Then the strength settings, they affect many key features of the drone: its ruggedness, overall weight, vibration handling, and most importantly, the resonance frequencies of the fuselage. For FPV drones, the goal is to achieve high stiffness, low weight, and resonance frequencies above 100 Hz. If the resonance falls too low, tuning becomes much harder, and flight performance can significantly suffer. Stiffness and resonance frequencies generally improve with more material, but this comes at the expense of increased weight. It's a delicate balance. Finding the right compromise can be tricky, especially since I'm not planning to redesign the fuselage at this stage. There's still a bit of trial and error involved until the drone is in the air for test flights. I don't want to make the structure too light and flexible. In the worst case, this could cause immediate oscillations or a flyaway that can't be fixed by filtering or PID tuning. That said, this isn't my first drone built this way, so I have a fairly good sense of what should work. To start, I'll slightly adjust the stiffness by modifying the top and bottom layer counts from the default slicer settings. I'll also switch the infill pattern to triangles, which offer good structural strength, and experiment with infill density to see how it affects the overall frame weight. For this build, I've chosen the following settings from the defaults: top shell layers, 2 mm, bottom shell layers, 2 mm, infill pattern, triangle, infill stiffness, 25%. Finally, it's time to print. Before starting, this part will require some support. Since the part is best printed vertically, the most effective option is to use tree supports. Tree supports provide excellent stability while minimizing material use, which is crucial for maintaining a clean finish on the final part. With the current settings, the print is expected to take about 7 hours to complete. After a successful print, the next step is to carefully remove the support material. Tree supports usually come off fairly cleanly, but I still take my time to avoid damaging any details on the part. Once the supports are cleared and the surface checked for any issues, I can move on to preparing and printing the next component in the build. When printing the drone arms, the primary goal is to make them as stiff as possible. Since they're made from plastic in this build, some degree of flexibility is inevitable compared to carbon fiber or metal. To maximize rigidity, I'm using the same PLACF filament as in the fuselage. It offers increased stiffness while still being easy to print. As with the fuselage, I've adjusted the print strength parameters to achieve a stiffer result. These include tweaks to shell thickness, infill pattern, and density to ensure the arms are as solid and vibration resistant as possible. To further reduce vibrations, I've added thin TPU layers on both the top and bottom sides of each arm. TPU, being softer and more flexible, is intended to act as a damping layer, helping to absorb some of the motor-generated oscillations. It also provides a cushioned interface between the motors and the stiffer PLACF frame underneath. At this point, I don't have concrete data to prove how much of a difference this makes. It's a bit of an experiment, but based on the behavior of the materials, it seems like a practical approach to improving vibration handling without significantly compromising overall stiffness. The arms printed well, and overall, the stiffness should be fine. I had previously tested a version made from PETG, but it turned out to be far too flexible for this application. In comparison, the carbon fiber reinforced PLA is noticeably stiffer and provides a much more solid, confident feel. While it probably won't withstand a major crash without breaking, the arms are simple to reprint and replace, making that trade-off acceptable. Okay, next the battery cover. It is a bit delicate, so I printed it in PETG instead of PLA, which I used for most of the other drone parts. PIG is a bit more flexible and less brittle than PLA, which makes it a better fit for something like this. The cover is mainly just there to improve aerodynamics and give the battery some light protection so it doesn't need to be super strong. Still, I want to be careful pulling it off the plate. Sure, it's quick and cheap to reprint if it breaks, but I'd rather not waste the time or material. TPU would actually be a good option for this too. Next up is the bottom cover. Its main role is to protect the electronics from impacts, debris, and rough landings. It needs to be strong enough to withstand hits, but at the same time, a bit of flexibility is actually beneficial. It helps absorb shocks and can also dampen some of the vibrations traveling through the frame. For this part, I used a combination of PETCF and TPU. PETCF provides the necessary stiffness and durability, while TPU adds a layer of flexibility that helps cushion impacts and also aids in damping vibrations, reducing the amount of mechanical noise reaching the sensitive electronics. Alright, time to weigh each part individually. The goal is to keep the total dry weight of the drone under 500 grams. First up, the fuselage. This holds most of the structural weight. It came in at 129 grams. I had hoped to bring that down closer to 100 grams, but considering the stiffness and durability it provides, that's still acceptable. Next, the arms. Together they weigh 103 grams. The bottom cover weighs 23 grams, and the battery cover comes in at the same, 23 grams. Now let's fit everything together for the first full assembly. While I've already test fitted these parts during the build process, this is the first time I've put the entire frame together at once. Everything fits as expected. No surprises there. The final weight of the fully assembled frame is 278 grams. That's a bit more than I originally estimated, but the added stiffness should pay off, especially when it comes to avoiding issues in filtering and PID tuning. With this base, I still have some headroom to stay under the 500-gram target once the rest of the components are added. Alright, at this point, I've gone through the design process and the printing of all the main parts for the drone build. Next, I'll move on to the electrical components, the parts I've selected for this build, and how they come together to create a fully functional FPV drone. This section will cover the key electronics like the flight controller, ESCs, motors, video system, and how they are installed and integrated into the frame to bring the drone to life. Let's take a closer look at the components I've chosen for this build. At the core is the SpeedyBee F4, 05VR 4BLS 55A 30x30 stack. It combines F4 flight controller and a 55 amp 4-in-1 ESC, easily handling high-performance motors on 6S. One of its best features is built-in Bluetooth support, allowing easy tuning, firmware updates, and configuration directly from a mobile app. No need to connect a laptop in the field. For motors, I chose T-Motor P2207V 3.02080 kV units in blue. These are solid mid-sized motors known for strong torque, good efficiency, and durability, ideal for freestyle or aggressive flying where quick throttle response is important. The video system uses the Caddx Vista Nebula Pro, connected with a 12cm cable. It's part of the DJI digital FPV ecosystem, offering a sharp HD video feed with low latency, giving a much clearer and more responsive flying experience compared to analog systems. For GPS capabilities, the build includes a JEP-RC GEP-M10 Nano GPS module. It's small, lightweight, and fast to lock satellites, making it a good fit for features like GPS rescue without adding significant weight. The control link is handled by the TBS Crossfire Nano RX, a trusted long-range receiver. It provides a reliable, low-latency connection even in challenging environments, perfect for flying far beyond typical line-of-sight distances. Build is powered by a Taidu R-Line 5.06 S1 400 mAh 150C LiPo. This battery seems to offer nice discharge capabilities, ensuring stable voltage under heavy loads and enough punch for high current maneuvers without sagging too much. For the propellers, I chose HQ Prop 5129R29, offering a good balance between thrust, efficiency, and control, matching well with the motor and frame setup. The entire frame was 3D printed using a combination of TPU, PLA-CF, PETG-CF, and PLA. Each material was selected based on the part's needs, TPU for flexible impact zones and carbon fiber reinforced filaments for strong rigid frame parts. Various wires, connectors, screws, nuts, and chemicals like thread locker were used to complete the build, ensuring all parts stay securely in place. Battery mounting is handled with an Ethics Power Strap 230, which provides a strong secure hold without adding unnecessary weight. For visibility, I added two Betaflight Pavos series Cobb LED strips, offering bright and clean lighting, and one TBS Satellites V1 for extra rear illumination, making the drone easier to spot during flight. Once all components are assembled and wired into the drone frame, the top of the frame looks like this. The battery is secured with a 1mm soft layer underneath to prevent movement, adding just enough grip. The TBS LED status indicator is positioned at the end of the frame, where transparent filament strips allow the light to pass through. The GPS module in the back of the drone is secured with double-sided tape, and the battery strap runs through strap holes inside the fuselage for a secure hold. The bottom side of the frame looks like this. The video antenna is neatly assembled inside the frame for optimal protection and positioning. Both the video receiver and FC stack are hard-mounted directly to the frame, ensuring a secure and stable connection. The radio receiver antenna is discreetly tucked behind the drone, positioned just behind the GPS module, helping to maintain a clean and organized layout while ensuring optimal signal reception. The capacitor is securely pinned between the fuselage and the bottom cover, preventing it from causing any additional vibrations during flight. Here are the diagrams showing how everything is connected. On the left side is the flight controller FC diagram, with all unused connections faded out for clarity. For the air unit, in this case a CADX Vista, the SBUS wire is not connected, as this build uses a TBS Crossfire receiver instead. On the right side is the ESC wiring diagram, showing the connections between the FC, motors, and the XT60 battery connector. Okay, let's put everything together and measure the total flying weight of the drone with a 224-gram battery. The full weight comes to 803 grams. By subtracting the battery, we get a dry weight of 579 grams for the drone itself. That's 80 grams more than the minimum goal was, but I think still quite reasonable for this type closed body frame 3D of build. That 80 grams could be easily tuned off from the prints, but with proper tuning, it should fly well. That wraps up the building phase of this video. Next, we'll bring the drone to life by powering it on for the first time and moving on to the initial ESC and flight controller configuration. Alright, it's time to power things up. For this initial stage, I'm not using a lithium polymer battery. Instead, I'm powering the system with a 100-watt 24-volt DC power supply. This setup is a bit safer at this point in the build because it can't deliver the same high current levels as a LiPo, which reduces the risk of components exploding or catching fire if something is wired incorrectly. Of course, the propellers are not installed yet. Safety first. Everything seems to power up as expected. The flight controller LEDs light up, the ESCs play their startup tones, and the CADX video transmitter shows solid green status lights. So far, so good. Next up are the motors. To configure and test them, I need to power the drone and connect it to my computer with a USB cable so I can use Betaflight. In Betaflight, I can check that each motor spins in the correct direction and is mapped to the right motor number. Very important. Before doing anything with the motors, make sure the propellers are removed. Spinning motors with props on during setup can be dangerous. Even a small bump in throttle can cause serious injury or damage. Another thing to watch out for is the CADX video transmitter. It gets hot quickly when the drone is powered on but not flying, since there's no airflow to cool it down. To avoid overheating, I place a small fan near the drone during motor setup and tuning. It helps keep the components cool and safe while working on the bench. Before configuring the motors in Betaflight, it's a good idea to update both the ESC and flight controller to the latest firmware versions. Keeping the firmware up to date helps ensure stable performance, compatibility, and access to the latest features. For the ESC, I use an online tool to flash the firmware. In this build, I'm using BlueJ firmware, which is well suited for 8-bit ESCs and helps get the best performance out of this lightweight stack. I flashed the latest version of BlueJ firmware to the ESC using the default settings. There's no need to change anything at this point. The defaults work well for most setups. If I run into any issues later on, there are tuning options available in BlueJ, but in most cases, those adjustments aren't necessary. The rest of the ESC configuration, like setting motor direction or enabling features like bidirectional D-shot, can be done directly in Betaflight. Next, I updated the flight controller to the latest version of Betaflight. The process is almost as simple as flashing the ESC firmware. First, you need to identify your specific FC target. Betaflight Configurator includes an auto-detect option, or you can manually select the correct target from the drop-down list if you know it. Before actually flashing the firmware, you have the chance to customize the firmware build. Betaflight lets you enable or disable various features depending on your setup. For example, you can choose to include or exclude support for analog video, servos, barometers, or LED strips. For this build, I only included the features I need to save flash memory and reduce unnecessary processing load. If you're unsure, the default selections are usually a good starting point. To flash, the FC must be put into bootloader mode. To do this, you press and hold the boot button on the flight controller while plugging in the USB cable. Once in this mode, Betaflight Configurator will detect the board and enable firmware flashing. After the update, the FC restarts with the latest Betaflight firmware and is ready for configuration. Now that both the flight controller and ESC are updated to the latest firmware versions, I can move on to configuring the drone. It's also worth mentioning that at this point, I've updated the CADX video system and the Crossfire receiver to their latest firmware as well. However, I won't be covering those update steps in this video. First up is the gyro orientation. Right away, I noticed that Betaflight thinks the drone is upside down, and the yaw axis appears to be 90 degrees off. That needs to be corrected so the flight controller accurately reflects the drone's real-world orientation. This adjustment is made under the Configuration tab, in the Board and Sensor Alignment section. I set the roll offset to 180 degrees. This flips the drone upright, and then set the yaw offset to 90 degrees to correct its heading. After applying those changes, the on-screen drone image now matches the physical orientation of the real drone, just as it should. This is also a good time to calibrate the accelerometer. Doing this not only ensures accurate angle readings, but it also gets rid of that annoying warning that pops up every time I connect to Betaflight Configurator. Just make sure the drone is sitting on a level, flat surface before starting the calibration. Next, it's time to configure which hardware is connected to which ports. Based on the flight controller layout, the Caddx video system is wired to UART1, so I enable UART1 in the Ports tab and assign it to VTX. This setup only handles OSD telemetry, things like voltage, flight time, and warnings. The actual video feed is sent directly from the Caddx unit to the goggles. If OSD data doesn't appear, this is the first place to check. Make sure the correct UART is enabled and configured properly. The ESCs already seem to be correctly set up on their assigned port, so I'll leave those as they are. The final step here is to enable UART6 for the GPS module. I'm not touching the other UARTs since they're not in use and already stable. After hitting save and reboot, it's a good idea to go back and double check that all port settings were actually saved. If something wasn't saved, it usually means there's a conflict or limitation. For example, Betaflight won't let you assign two different functions to the same UART or enable combinations that your flight controller doesn't support. In my case, everything looks fine, and all settings saved correctly. So now the fun part, bringing the motors to life. Again, never do this with props on. It's dangerous and can easily cause injury. Use smoke stoppers or a current-limited power source, like I do, to stay safe during initial tests. Before spinning up the motors, there are a few initial settings to check. Since my ESCs run BlueJay firmware, they support DSHOT, including bidirectional DSHOT, and I've set it to DSHOT 300. This is important because it allows the use of RPM filtering, which is essential in almost all modern FPV builds. Make sure to enable both bidirectional DSHOT and RPM filtering. Also, it's good practice to set the correct motor pole count so that the telemetry gives accurate RPM readings. Regarding the ESC sensor setting, it's not needed if you're using bidirectional DSHOT, as with BlueJay firmware, because RPM telemetry is transmitted over the same signal line used for motor commands with no extra telemetry wire or UART required. So in this build, ESC sensor has no effect. First, we need to tell Betaflight how the motors are physically connected to the ESC. Basically, which motor is in which position on the drone. This step is important for proper flight behavior, as Betaflight needs to know exactly where each motor is located to apply the correct control logic. To do this, we use the motor test tool in the Betaflight Configurator. By spinning each motor one at a time and watching which one actually rotates on the frame, we can match them to the correct motor number in the Betaflight layout. Next, we need to set up the motor directions. The motor's direction is determined by how the three motor wires are connected to the ESC. In many cases, the wiring can end up being random, as it's often difficult to follow each wire from the motor to the ESC. This was the case in my build. Fortunately, this is not a problem because you can change the motor direction easily through software configuration, so there's no need to worry if the direction isn't right initially. I prefer to set the motor direction manually, rather than using the wizard. This gives me more control and allows me to ensure each motor is set correctly. I go through each motor one by one, and while spinning the motor, I use my finger to feel the direction of rotation. This can be tricky to see visually while the motor is spinning, so feeling the direction with my finger is a simple and reliable way to check. After saving the configuration, it's a good idea to spin the motors for a longer period to confirm they're all running correctly. At this point, I also listen closely to each motor and observe for any unusual vibrations. If there are motor issues, such as irregular sounds or excessive vibration, it's a good early warning that something might need adjustment or that a motor may be faulty. I also wanted to add a status LED to the drone, so it needs to be configured in Betaflight. In this case, I'm using only a single LED, so the setup is quite simple. First, I go to the LED strip tab in Betaflight Configurator and switch to wire ordering mode. Then, I click any position on the grid to place the LED. Once placed, I set its function to color and choose green as the base color. To make the LED more useful, I also enable the overlay warning function. This allows Betaflight to display basic status information using the LED, for example warning signals or arming state, which is handy during setup or when flying without a full OSD view. Now is a good time to check the controls. Everything should work fine with the default settings, but it's still important to verify that all inputs respond correctly. I go to the Receiver tab in Betaflight and make sure that throttle, yaw, pitch, and roll are moving as expected when I move the sticks on the transmitter. This quick check helps ensure there are no issues with channel mapping or signal reception before moving forward. Next, I move to the Modes tab in Betaflight, where I configure how different buttons on my controller trigger specific flight modes. This step is essential to ensure safe and controllable flight behavior. I already have my preferred switch layout on the transmitter, so there's no need to rethink the control scheme. First, I set up the ARM function. I assign this to AUX1. To do this, I select ARM from the mode list and click Add Range. Then, I either choose AUX1 from the drop-down menu or simply press the desired switch on my transmitter. Betaflight detects the signal and sets the correct AUX channel automatically. After that, I define the range of values that will activate arming. Since the switch I'm using has only 2 states, it's easy to select a clear and reliable value range, in my case when the switch is fully flipped down. Next, I add angle mode. This is useful for flying line of sight or doing basic tests, where full manual acro control isn't needed. It gives a level self-balancing mode, which can help avoid crashes during test flights.
Flight mode cruise. Flight mode acro.
Then, I set up GPS rescue mode. Hopefully, I'll never need it, but it's an essential safety feature. If I lose signal or visual contact with the drone, this mode can automatically bring it back to the launch point. Finally, I configure the OSD disable mode. This is useful when I want to fly or record video without the telemetry overlay, giving a cleaner image feed from the FPV camera. Final checks, and I am done here.
Engine off. Flight mode cruise. Flight mode acro.
OSD, on-screen display settings in Betaflight, allow you to overlay important telemetry data directly onto your video feed while flying. This gives the pilot real-time information about the drone's status without needing separate displays or interfaces. The OSD settings should include a few mandatory telemetry values. These are the cell voltage indicator, which shows the average voltage per cell, and the radio link quality and strength, both critical for maintaining control and avoiding signal loss. Altitude is also important, as most countries now have regulations on how high drones can fly depending on the airspace. Since this drone is equipped with GPS, I've enabled the home direction indicator, which is useful when flying farther away or in unfamiliar areas. Location would also be helpful for finding a lost drone after a crash, but that information is also stored in the flight controller logs, so it's not strictly necessary on screen. I try to keep the OSD clean and uncluttered, showing only the essentials that help with safety and navigation. One key item that should always stay on is the drone status message, which is selected as default in Betaflight. It provides real-time feedback on the drone's state, including arming status, warnings, and GPS lock. It's crucial for monitoring the system during flight and reacting quickly if something goes wrong. In this section, I'll go through Betaflight filter tuning and PID adjustments. I perform multiple short test flights, analyze the logs, and tweak the settings to reduce vibrations and improve stability. After each flight, I adjust filters and PID values step by step until the drone flies smoothly and responds well. So, before the test flight, it's important to ensure that we can record flight data for later analysis. In this case, that means installing an SD memory card into the flight controller. This particular FC doesn't have any internal memory available for logging, so the SD card is essential. Using an SD card also has the advantage of offering much more storage capacity than flight controllers with built-in memory. That means I won't need to constantly erase old flight logs and can keep more flight history available for reviewing performance, tuning, or diagnosing any issues that come up. Okay, now we're at the stage of the build where we can prepare for the first test flight, which means it's time to install the propellers. This is also a point where things can go very wrong if not done carefully. I strongly recommend double-checking the direction of each prop. Installing them incorrectly can cause the drone to flip on takeoff or behave unpredictably. The key is to check which side of the propeller is facing up. Usually, the side with the text or model number should be on top. More importantly, make sure the leading edge of each prop faces the direction that the motor is configured to spin in Betaflight. Take your time here. A quick mistake can result in a broken drone before you even leave the ground. In the first test flight, the main goal is to verify that the drone operates correctly, that all systems work as expected, and to gather data on vibrations and potential electrical interference affecting the flight controller and gyro. I perform a steady hover while listening to motor behavior and watching for any odd movements. With Betaflight's default settings, a 5-inch drone should be stable enough to fly safely without major problems like flyaways. The drone seems to fly okay overall, but the motors sound a bit rough, which could indicate noise reaching the gyros. Well, the black box logs will reveal more about that next. Let's take a look at the logs, especially focusing on potential gyro noise. First, the log files must be downloaded from the drone's SD card using the black box tools in the Betaflight Configurator. Once downloaded, they can be uploaded into Blackbox Explorer for analysis. Blackbox Explorer allows us to view the frequency spectrum of the gyro data across the pitch, roll, and yaw axes. While all three are important, noise issues typically show up most prominently on the pitch and roll axes. Here, we're looking at the gyro-measured noise after filtering has already been applied. In an ideal case, we want little to no noise above 60 Hz. This is because real flight movement mostly happens below that threshold. Frequencies above 60 Hz generally represent unwanted noise, often caused by mechanical or electrical issues. In this log, I immediately notice a sharp peak around 100 Hz. That's a clear sign of unwanted noise. Common sources for this type of resonance include loose components, antennas, wiring, motor mounts, or arms. After ruling out other possibilities, my current suspicion is that the arms are the culprit, though I can't be 100% sure yet. The second best option, when hardware changes aren't ideal, is to improve filtering. Since this is a narrow and specific frequency spike, a notch filter is the best for this. However, the default notch filters might not target frequencies as low as 100 Hz, so adjustments are needed. The downside? The lower the frequency we try to filter, the more delay it adds to the PID loop. And that affects flight feel. Pilots often describe this as how locked in the drone feels, meaning how precisely it responds to control inputs. So it's always a balance between noise reduction and flight responsiveness. Let's make a few careful filter adjustments. Small changes only, as large shifts can lead to unpredictable results. First, I disable the first of the two gyro low-pass filters. With modern flight controllers, this filter isn't really necessary anymore. Next, I turn to the dynamic notch filters. By default, the notch count is set to 1, meaning Betaflight will track a single peak frequency. Since I've only observed one significant spike so far, I'll leave this unchanged. However, the minimum frequency is set to 100 Hz, and the spike I identified earlier was around 95 Hz. To catch that noise, I lower the min frequency to 90 Hz. I also reduce the max frequency to 400 Hz, narrowing the scan range and slightly reducing PID loop latency. With these changes made, I'll take the drone out for a second test flight and see how they affect performance. Immediately, I can hear a clear difference in the motor sound. The drilling sound is gone, which is a good sign. Let's compare the video recording from this flight with the first test flight. Log analysis confirms that the 95 Hz spike is almost gone across all axes. Before continuing with the PID tuning, I'll widen the notch filter slightly to see if we can eliminate the remaining noise completely. This should give us a cleaner signal and a more stable baseline for the next tuning steps. And once again, a short test flight is needed to collect fresh data and confirm the effect of the updated notch filter settings. It looks like we've gotten rid of the 95 Hz frequency spike. Let's hope that doesn't cause problems later. Now that the initial filtering is tuned and all frequencies look nice and clean, we can move on to PID tuning. I say initial because as we push this build closer to its performance limits, we may need to adjust the filters again. In this method of PID tuning, the first goal is to find the perfect PD ratio for this build. This involves a series of flights with different PD ratios. It's also crucial to set feed forward to 0, as data won't be valid for tuning otherwise. The I term and dynamic dampening affects the results as well. They need to be set to 0. Betaflight's default settings are tuned for 5-inch drones, so I'm not expecting drastic differences from the defaults. I begin by lowering the damping from 1 to 0.6. I expect this to add too much damping, but it serves as a starting point. After that, I perform a series of flights, gradually increasing the D with each flight and record the logs for analysis. I use the SpeedyBee flight controller's integrated Bluetooth along with the mobile app to adjust the PD ratio between flights. It's a quick and convenient way to update the drone's configuration. No need to deal with USB cables or hassle with OSD menus and goggles between each flight. Now I have a data file from each flight with a different PD ratio so I can compare their performance. There's a free software called PID Toolbox that helps analyze flight data and find the optimal PD ratio. First, all the log files need to be downloaded from the drone and loaded into the tool. Then, using the software's step response feature, I can compare the response curves and evaluate which tuning performed best. In the PID tuning process, I focus on analyzing the step response curves for both the roll and pitch axis using the PID Toolbox. The goal is to find curves that follow the setpoint line, value 1, as closely as possible. Ideally, the response should rise quickly to the setpoint without overshooting, then settle smoothly with minimal oscillation. This indicates well-balanced PID values. Once selected, I enter these P and D values into Betaflight. Next, the goal is to push the P and D values as high as possible, without changing their ratio, to make the drone as responsive and locked in as possible. This is done using the Master Multiplier slider in the PID Tuning tab of Betaflight. Instead of adjusting individual values, this slider increases all PID terms proportionally, preserving the tuned balance between P and D. I approach this by running a series of test flights, gradually increasing the slider step by step. I begin at 0.9, carefully observing the drone's behavior during each flight. A key part of this test is listening closely to the motor sound. If I start hearing high-pitched oscillations, grinding, or a drilling noise, it's a clear sign that I've gone too far. At that point, I stop. Going further could risk damaging the ESCs or motors due to overheating or excessive stress. And we're back in PID Toolbox for analysis. Once again, I use the step response tool to evaluate the control response curves. I'm looking for a sharp rise to the set point and a flat, stable line afterward, without excessive oscillation. In the current test flights, some of the curves show visible oscillations, while others track the set point more cleanly with minimal deviation. At this stage, I choose the curve that looks the most stable and controlled. Later on, when I start pushing the drone to its limits, I can fine-tune further based on flight feel, motor temperature, and sound. A small amount of oscillation might be acceptable if it results in better responsiveness or reduced filter delay. But for now, since this is a fully DIY build, I'm playing it safe and selecting the most stable result to lock in the gains. Also, I'm still a bit concerned about the 95 Hz spike I filtered out earlier. While it's currently suppressed, I'll keep monitoring it closely in future flights to make sure it doesn't resurface. I select this curve. It looks clean and free from noticeable oscillations, indicating a stable response. However, I think the P to D ratio is still slightly off. The response feels a bit too dampened, suggesting that D might be slightly overpowering P. To correct this, I'll adjust the ratio by reducing the D gain by one step while keeping P the same. This should sharpen the response slightly without introducing instability. Next, we move on to tuning the I term. The I term, or integral component, works iteratively. It gently pushes the drone toward the target set point after the P and D terms have done their fast corrective work. It's essential for maintaining stability over time, especially in windy conditions or during slow, sustained movements. Just like before, I'll start with a baseline value, perform a series of test flights, and analyze the logs to see how well the drone holds its attitude over time. This process helps find the sweet spot where the I term is strong enough to correct drift but not so strong that it causes sluggishness or oscillations. Once again, I analyze the step response curves, looking for the sharpest and flattest response. The ideal outcome. I can clearly see that correcting the PD ratio earlier during the master multiplier tuning was the right move. The drone now reaches the set point more accurately. The current curve looks solid. I did consider reducing the damping slightly on the pitch axis, since it's still lagging a bit behind the set point, but I've decided to leave it as is. The response is acceptable, and the system looks stable. I'll input these finalized PID values into Betaflight and proceed to the next step of the tuning process. Now I've reached the stage where it's time to prepare the drone for its first real flight. One of the most important final tuning steps in Betaflight is enabling and configuring feed forward. Feed forward is a crucial feature that improves responsiveness. Normally, when you move the control stick, the PID loop takes a short moment to react. This delay can make the drone feel sluggish. Feed forward helps by directly responding to rapid stick movements, bypassing the PID loop's delay. It gives the drone an immediate push in the desired direction toward the set point, and once the PID loop catches up, it takes over smoothly. The result is a snappier, more locked-in feel during flight. However, too much feed forward can cause overshooting or twitchy behavior. As a conservative starting point, I've set the feed forward gain to 1.0. This might be on the lower side, but it's a safe baseline. After a few extended test flights and blackbox log reviews, I'll fine-tune it further based on the drone's real-world response. I also set the dynamic idle value to 20. This setting helps reduce prop wash in certain flight situations, particularly when quickly dropping the throttle to 0. Without it, the props can nearly stall, causing instability or wobble, especially during aggressive descents or sharp turns. By keeping the motors spinning just slightly faster at idle, dynamic idle ensures smoother transitions and better control when the throttle is momentarily cut. Next up are the rate profile settings, which define how stick inputs are translated into drone movement across all axes and throttle. Every pilot has their own preferences here. While I haven't flown extensively, I prefer a setup where all axes use the same rates and I have fine control through most of the stick range, with the response ramping up sharply near the end. This gives me smooth, controlled handling during normal flight using wider stick movements, while still allowing for quick, aggressive maneuvers when I push the sticks to their limits. For the throttle curve, I prefer it to be linear. This gives me direct control over the throttle input without any adjustments at different stick positions. While I could limit the max throttle, I don't feel the need to hold back my build. Max power reserve is what I prefer. Last but not least, the fail-safe settings. These are critical, especially when flying outdoors. In Betaflight, you have 3 options: drop, land, and GPS rescue. Since my build includes a GPS module, I've chosen GPS rescue. The failsafe activates in 2 scenarios: loss of controller signal manual trigger by pressing the previously assigned failsafe button on my controller. When triggered, the drone will automatically rise to a preset altitude, in my case 50 meters above the arming height, and then return to the home location, which is also set at arming. There are several detailed GPS rescue settings in Betaflight that I won't dive into here, but it's important to note, misconfiguring these can cause a crash. Still, despite its complexity, this feature could one day save the drone, so it's absolutely worth setting up. And of course, it's wise to test it under controlled conditions using the manual trigger. Now it's time for a real test flight. And of course, it's over the lake. That means if something goes wrong, the drone is likely gone for good, straight to the fish. No pressure. This flight is different from the earlier short test flights. Now I'm focusing on sharper maneuvers and heavier throttle use. This kind of flying provides valuable data to evaluate how well the drone behaves after all the tuning, especially under more demanding conditions. The key thing I'm looking at is how closely the drone follows the set point. The set point tells the drone where it should be, and the gyro tells us where it is. The smaller the difference between the two, the better. To get meaningful data, I apply fast full-stick inputs, like quick rolls, which show up clearly in the logs. Looking at the data, I see a bit of undershoot at the beginning and overshoot at the end of the movement, but otherwise the set point is followed quite well. This suggests the general tuning is close. I also review how feed forward behaves during these sharp moves. It seems to do its job, but I think increasing feed forward slightly might help reduce that overshoot by commanding harder right at the start and end of the movement. This could improve response without relying as much on the slower PID corrections. Here we see the same in the second roll. Slight undershoot at start and overshoot at the end, but good set point tracking overall. A small bump in feed forward should improve responsiveness and minimize that. Then let's look at the noise. From the unfiltered gyro data, there doesn't seem to be much noise. It actually looks like a pretty clean build. I really pushed the drone during that flight, and even with strong wind gusts up to 15 meters per second, so some of the low-frequency movement may be wind-related, and I think that shows here also a bit on low frequencies. Nothing alarming though, so think I will reduce filtering slightly. Motor RPM-related vibrations are clearly visible here, just as I expected. In the unfiltered gyro data, I can see 2 out of 3 peaks, which are the result of the motor RPM. These are filtered by the RPM filters in Betaflight, which track the motor RPMs. Since see 2 peaks and not expect 3, due to my 3-blade prop setup, I can reduce the filtering power of the middle one to 0%. For the other 2, I think can lower the filtering slightly to around 90%. This will reduce filter delay and improve the drone's responsiveness. There's some noise coming, trot the filters around 100 Hz, but it's not bad, and the notch filter is handling it quite well, so no changes are needed there. RPM filters, along with other settings, can be tuned from the Betaflight Configurator. To adjust the filter weights for RPM, I set them to 90, 0, and 90. Remember to click Save and then press Enter to apply and save the settings. To minimize the under and overshooting observed in the logs, I'll increase the feed forward slightly and evaluate the effects in the next test flight. Then I adjust a few settings that don't impact flight performance but improve the OSD's usability. First, I tune the low battery warnings and alarms. Because the motors are high performance and draw a lot of current, they cause noticeable voltage sag during throttle punches, which can trigger annoying battery warning messages. To reduce this, I set short delays, just a few seconds, for both warnings and alarms. Next, I address the RSSI signal strength warning threshold. The default is negative 60 decibels milliwatts, which is far too high for a around 900 MHz TBS crossfire receiver. A more suitable value for my build is minus 105 decibels milliwatts. This threshold can vary based on your radio system, frequency, and packet size. Smaller packets generally tolerate lower signal strength before connection is lost. It's best to refer to your radio controller's documentation. With this setting, the RSSI value will blink on the OSD when the signal drops below negative 105, indicating a risk of failsafe activation. I also prefer to see the consumed current alongside cell voltage on the OSD. This gives me better situational awareness of my battery status and remaining flight time. Aggressive flying causes higher current draw, which is easy to monitor by watching the milliamp hours (mAh) consumed. However, for this to be useful, the current sensor needs to be properly calibrated. That means the scale value in Betaflight must be set correctly so it shows accurate readings. The simplest way to do this is fully charge a good battery. Fly it and take note of the milliamp hours consumed shown in the on-screen display. Recharge the battery fully and check how much charge it actually took. Use these values to calculate a new scale factor and update it in Betaflight. You can repeat this process a few times to refine the accuracy. Since I've invested a lot of time and effort into this configuration, it's important to back everything up before moving on to the final test flight. I don't want to risk starting from scratch due to some unexpected issue. This finalizes the tuning process for the second test flight, bringing this video close to its finale. Before we wrap up, I want to acknowledge something important. Tuning an FPV drone can be an endless iterative process. Experienced pilots are able to fly right on the edge of a drone's performance envelope and fine-tune it based on feel, how responsive it is, how locked in it behaves, and how it handles under pressure. I'm not quite there yet. I can't push the drone to its limits in a controlled way, so I'm not able to tune it to absolute perfection. But that's okay. My expectations are aligned with my current skill level. If the drone flies well for me, then that's good enough, for now. As my skills improve, I'll come back to my builds and push them further. That's part of the learning curve. And more than anything, this is a fun hobby. I hope you found this video as interesting and useful to watch as it was for me to make.